This particular section is the longest of them. The last one that we're going to do on Friday is the shortest by far. I may add something. I'm not sure. I haven't gotten that far into it, but right now it's only like 12 slides, which is like quite a few less than what you're used to. For the opener, which state of matter of water, the water doesn't hit the plasma state. It doesn't. Which state of matter of water has the most energy? Which state of matter?
Liquid.
No.
Wait, no. Wouldn't it be water?
Okay, so that's called what? Okay, so well, if it's with added heat, it's steam. Okay, but the like boiled version, what do we call it?
Gas.
It's the gaseous state. Okay, we call it water vapor. If it's a natural state, it's evaporation. Okay, makes clouds. If it's with heat, then that's boiling. That's the hot stuff that can tear your flesh off your skin if you're not careful. What does the amount of energy, okay, so what does kinetic energy do to the temperature of water? What happens if you add or you remove energy to water?
Like either freezes or steam gas.
Okay, it either heats up. If you add kinetic energy, which would be from, you're starting from solid, which is ice, first we change it to water and then we change it to gas. If you remove it, then it would do the opposite thing. And we're actually doing water in both my art space and my chemistry class right now. It's odd that it lined up right on the same day. Like I said, this one's a little on the lengthy side. We have actually covered in this hydrosphere and atmosphere section that I'm doing before next week. We've covered a bit of this from time to time. So it's been a while since we've done the atmosphere and the different spheres of this planet, but they're coming back. We're just going to be going more in depth with water. And yes, we're going to talk about winds, which is technically the atmosphere, but they're tied into the tides and ocean circulation. That's the kind of stuff we'll talk about this week. You should know a little over 70% of the surface of our Earth is covered in water. This is not something that's new. This is probably something that you've had multiple years as you guys have been going through school. Of the water that's available on our planet, most of it is ocean or salt water. It's stuff that you cannot drink without processing it first, or it will kill you. It will dehydrate you. So that means that there's only about 3% of water on this planet that's fresh. Now, most of that is locked in ice. This is all stuff that we did last semester. It's just been a while. Okay, so with our fresh water, most of it's in glaciers, the ice caps, snow, sea ice, that kind of stuff. Groundwater, if you have a well, okay, the stuff that's underground that we have to be able to pull up is about 0.4%. That's most of the liquid fresh water that we have, but you have to be able to access it. I said you may have a well of some type on your property. Some of the older homes, most of them did. What you think of as rivers and lakes is only 0.05%. That's the available on the surface fresh water. And then the other 0.05% is in the air that we breathe, okay, or it's within the dirt itself. Not considered, it didn't blow up, but not considered groundwater. So this is this is a little bit more in depth than when we broke down how fresh water is available on our planet. Anyway, you aren't around in the first semester. I have some students that are only taking the second half of ESS, or maybe just didn't get it in the first place. This is sort of a refresher of, I can't remember if it was the second or the third 6 weeks that we did weather and atmosphere. I have to go back and look at my stuff. We're still typing. Let me double check online. Nitrogen in it? Okay. Okay, I don't see anybody else new. You're still trying to get your Chromebook to work. Is it not connecting to the internet?
It's connected.
No, is it slow?
It's not working.
Oh, well.
I never responded.
Okay. Do a software reboot that works normally. Now, like I said, we're going to do the first 5 lessons with the hydrosphere unit. We're not going to do the actual water cycle until after next week. I can't even remember which specific things I had lined out, but there's another week's worth of material that are dealing with the interaction between the hydrosphere, the part that has water, and the atmosphere, the part that has air. It's just, it's quite a bit of material. All right, so there are multiple spheres on our planet. Water interacts with every sphere on this planet. Now, sometimes you've heard we call the lithosphere the geosphere. That's like the part we walk on the rocks, maybe the Earth itself. The atmosphere is where we breathe, okay, so the air portion above ground. Your biosphere, which is everything that's living, plant and animal. Okay, even bacteria is part of the biosphere. Viruses technically are not because they're technically not alive. The hydrosphere itself, duh, okay, that's where we find both our liquid and our solid water. And the cryosphere is the frozen water specifically. It's separate from the hydrosphere, even though technically the glaciers, when we talk about fluxes today, they are a part of the flux of energy with water molecules. And the cryosphere, the glaciers and the ice caps and the sea and all that stuff we talked about multiple times now, that has the largest contributing factor on the climate of our planet. How much water is locked in ice and how much is free, which is going to either raise or lower sea levels and is going to affect the currents of the ocean. And the currents of the ocean is what is the thermostat for a planet. You do not need to write this bottom thing. We've already gone through evolution and how glaciers affect where the shoreline, the coastline is. We've been talking about ice and water for quite some time. If I go too fast, let me know. I'm trying to make sure that we get through the whole thing because this is the big one. They get shorter as we go on through the week. But snow cover, freshwater ice, they're seasonal. That means they come and go when it gets warm enough. They come back when it gets cold enough. Most snow does not stick around in the next year. You've got to be much higher latitudes in order for that to stick. If you do have decent snow or ice in your higher latitudes, means more towards the North or South Pole, then that might stick around for a few years. But most snow and freshwater ice is completely comes and goes every single year. Not the ice caps, that's different. Just freshwater ice, the stuff that goes on ponds and lakes that people used to ice skate on when I was a kid. Your glaciers, your ice sheets, they mean the same thing. Permafrost is over land. We also call these tundras. I didn't really go that far into it because you should have done that with biology, I think is when you do all the different types of habitat, I guess. I don't know, I'm not a biology teacher. These can last for a long time. The ice sheet over Antarctica is millions of years old. It started 35 million years ago. The North Cap over the Arctic started about 3 million years ago. It's much newer and smaller. But most of our frozen water is locked over Antarctica. Obviously not all of it. But you have above the tree line, and then when you get into the snow line, when you go up high enough in mountains where there's no trees and there's ice everywhere, that stuff will stick around for a long time too.
So the glaciers, these are all freshwater?
Yeah. Frozen, like even if you take salt water and you freeze it, it pushes the salt to the outside.
Oh, really?
Yeah, the ice itself is fresh. It's one of the ways to get salt water salt out of salt water. The easiest way to do it though is to build a solar oven, if you will, and you put the water underneath it, and as it evaporates, it collects, and that's fresh water. And it leaves the salt behind.
Wow.
Yeah, it's just,
So
you can take just a regular old glass and mix up a whole crack, like a whole bunch of like regular old salt in it, and make it super, super salty, and just let it sit out and dry, and you're gonna get huge salt crystals left behind. That's all the water's from. That's it, like one of the, that's like 6th grade science project kind of stuff.
This is really cool.
Okay, well, water, like, extremely important. We would not survive if it was not for the special water or properties of water, which is why I gave you that question on Friday.
Wait, so how do they get salt? Like,
Salt is a rock that we mine from.
wait, really?
Yes, we talked about this when we did rocks.
Is
Yes.
salt from like salt water edible? Okay.
I mean, you don't want to drink it because then it goes straight into your system and it dries you out. Okay, I didn't blue out anything because there's so much on this slide. The properties of water. It is an excellent solvent. That means it will dissolve a whole bunch of stuff. Now, you should know by now that oil and water do not mix because one is polar and one is non-polar. You should have heard the phrase before, like dissolves like. That's more in my chemistry lesson. But water does have the ability to dissolve all different kinds of stuff. And it's something that does the dissolving is the solvent. The thing that is dissolved is the solute. That's more chemistry stuff. It's weird because I'm teaching this in both subjects. It has a very high dielectric constant. If you take a dielectric, it helps like get rid of excess things in your body. Like if you're too dehydrated, you're holding on to toxins. Naturally, what makes people sick because we don't drink enough water as a whole. It has very high surface tension. That's what lets leaves float on the surface, and those water bugs that legs stick out, like skirt across the top of it and not fall through. It's what makes it attracted to itself, and it makes water bead up. That's why water droplets they're not perfectly sphere, they're teardrop in shape, but it's attracted to itself. Its highest density is at 4 degrees Celsius, so that means, because it freezes at 0, 4 degrees Celsius sinks. That's part of what helps the ice to float. Besides, it traps air, it expands it, it increases the volume, and it decreases its density. And it has a very high heat of evaporation. That means it takes a lot of energy to take it from the liquid state and put it into the gaseous state. Or we'd have a hard time keeping liquid water on our surface. That's what's wrong with Mars. It has to do with how thick the atmosphere is. If you walk outside and you're not contained in your suit, you open your eyes, your tears boil out of your eyeballs. Because there's it has to do, there's so much about Mars that I don't know how they're going to send people there and they're not going to just die.
People live on Mars.
So many things wrong with Mars.
I have an idea.
But send robots?
No,
That would be a smart thing.
Death row prisoners.
Because they're going to be the smartest people that are going to understand the mechanics and the biochemistry and all the other stuff that's necessary to survive. No. I highly doubt, maybe 1 or 2, but I doubt it.
We can send monkeys.
We're not going to send monkeys to Mars. All right. You need a reservoir is something that contains water. It could be an ocean, a lake, a river. It could be anything that contains water. It doesn't have to be the liquid state. So that's what a reservoir is. Besides, you should know that reservoirs hold water and then we pull drinking water from it. Hopefully you know that word already. To anything that holds water is a reservoir. Technically, your body's a reservoir. I don't know if that one's open.
If I stick a straw in my skin, I can drink.
No, you cannot drink water out of your skin if you stick a straw in your skin. Your super surface, okay, so above, that's the stuff in the atmosphere. Clouds, they are obviously a place where water goes. Just the air we breathe in this area tends, as long as it's not cold, tends to have a higher humidity content, but the desert's gonna have a lower humidity content. So surface water, oceans, lakes, river streams, creeks, or if you're like me, we used to call them cricks. It's just like a deep connection. We had a conversation last night at Easter about the difference between a creek and a crick. An estuary, and then the big frozen parts that they stay frozen for a long time would be your glaciers. But sea ice goes in there. Anything that's frozen, essentially, I'm lumping in with glaciers into the cryosphere. Your subsurface water, okay, like I said, groundwater, you have to have some type of a mechanism to pull it out. And your most common thing that you're going to be exposed to is a well, whether you're sticking your like a literal bucket going down a rope to get it, or you've got a pump, which is what most people use. I used to have a well on my old property. It was awesome. And then Harvey came and it flooded the pump and it fried. And my tanks cleaned out and they floated and they snapped. I didn't feel like having a whole new well put in or a whole new pump. It was nice while it lasted. Now we're gonna come back after next week and we're gonna do like the different interactions between the different types of water systems. That's all part of the water cycle and eventually the carbon cycle. They're all interacting with each other. For the last 6 weeks, we're going to do the second half of the hydrosphere. This is a large unit. It's got this week and it's got the first week of the six weeks. I have to do, I don't know, I wrote it out. I'll tell you. You guys have most of this on your paper. You just don't have the book. And I couldn't get it to print right. I need to make sure that you can read one of these. I'll tell you here in a second. All right, so we have a reservoir. We have a lake, and its volume is 1,000 million liters, which is what ML stands for. Okay, so we have rainfall, because the stuff on the left is incoming and the stuff on the right is outgoing. We have 10 million liters per year of rainfall, and we have a river feeding it at 50 million liters per year. So we have a total influx, we're going to use the word flux a lot here, of 60 million liters per year. On the other side, we have natural evaporation at 30 million liters per year. There's a river leading out at 20, and then the groundwater outflow is 10. So 30, 50, 60 million liters per year. When your influx and your outflow are the same, this is called being in steady state. That means that this lake's volume is not going to change much. So you're going to have sometimes, so your input or influx, it equals the output, which this last example had, which you guys basically had on your paper, I just didn't have the box. This is called steady state. If your inflow is greater than your outflow or your input or your influx, I don't care which word you say. I have that like a fuzzy on my nose. I'm just doing my mask. Just doing my mask. If the input's greater than the output, you're going to have flooding in some way, shape, or form, which is always crappy. And then if your output is greater than your input, then your lake not necessarily is going to dry up, okay, but the water level is going to fall. Most lakes are at steady state or they wouldn't be here anymore. But yes, flooding is always going to be an issue if you live close to a body of water. Hopefully it's not anything major. But that's what that previous thing was on your paper towards the bottom. Yeah, towards the bottom. I just didn't draw the box around the lake. I think it worked. You still see the stuff, and I got lazy and ran out of time. If you know how much volume is in the lake, so I'm going to use the previous example. Now I'm on the back of the paper now. That lake had 1,000 million liters. That was its holding capacity. And you know how much water is flowing out total, which was 60 million liters, the inflow and the outflow are the same, then you can figure out what's called residence time. How old is the water on average inside that lake? So you're going to take the volume of the lake, which in this case was 1,000 million liters, ml, the outflow, which was 60 million liters, it's the same as the inflow, and then that's going to tell me that the average water inside that lake is 17 years old. That's how long it takes the water, which I know there's going to be some that gets out quicker and some that stays longer, but on average, that water molecule is going to be inside that lake as long as something doesn't drink it for 17 years worth of time. On average. And I know I've said this in some classes and not others. Everything on this planet is recycled. Every single atom on this planet has been somewhere in something in some way, shape, or form. Like the carbon in your body could have come from rocks, literally. The water that's in this coffee I just took a sip of has probably been drunk and peed out by, I don't know, multiple organisms, maybe dinosaurs, who knows? And then when I swallow it and it goes into my system, those hydrogen and oxygen atoms are now going to be used. Now, some of it gets, flushed out, but they're going to be used to create and mend like poison ivy I got on my hand helping my daughter Easter egg hunt yesterday. So this is I'm not trying to flip you off. It's on my middle finger. So when this heals, when this heals, then the things that I ingest may actually be replacing and creating the cells that are helping to mend this little cut that got poison ivy in it. Bless you. Let's see, kills, not killing. Because there's really not that much on this one. So residence time, the way that I use this in the case of that lake, if that lake becomes contaminated with something really nasty, it's going to take 17 years to naturally flush it out. That's what residence time tells you. There's only these 2 bullets on here. If you have a drought, okay, and you figure out how many million liters it has fallen, I'm not going to try to teach you the math behind that. It's not that hard. That will let you know on average how much time with natural rainfall it would take to try to replenish the lake. If you still have incoming, in the case of this example, your inflow and your outflow are the same. So you're either going to have to hope for excessive rains or snow melts for the places that live close to the mountains, or you're going to have to actually introduce water into it itself. And that would be more if you have like a private lake or private pond on your property. Most people just dig a hole and think the water's going to stay in there, and that's like not the way it works. You either have to have a river source that comes in and then an outflow, or you have to have like an actual, like a hose that feeds it. Then you got to take the chlorine out of the water because that burns the fish's lungs or gills. They don't have lungs. Well, I guess they have lungs technically, but they breathe with their gill. I know what I'm trying to say. Cannot put regular tap water in with your fish or kill them.
Really?
Yes.
That's why my fish always die.
You have to treat it. You have to put brine in it.
I just throw it in water.
Oh my gosh, you can't just throw fish in tap water. You burn their, anyways.
Oh my God.
So no, you have to go get it's called prime and it smells really bad and you only need like a capful for a 50-gallon tank. All right, so most of the heat on our planet comes from our star. Okay, so almost all of it comes from our sun. It comes through the atmosphere. It gets absorbed by the planet. Some of it gets bounced back off by clouds and by ice and snow. Once again, we've talked about it before. We're pulling everything together. This causes convection currents. Now we're going to start, I believe tomorrow is ocean circulation, and we're going to start at currents. It's a little bit more complicated. We're going to have a whole one on the Coriolis effect, which I could teach you the physics behind it, but I opted out of that. I will show you the basic equation for those of you that are interested. Let's see, where am I at? This fuels evaporation, precipitation, right? So just sort of introducing the water cycle. The sun heats water, naturally causes evaporation. It's not that the oceans are boiling, causes natural evaporation. That condenses in the clouds. They become heavy enough and the water precipitates back out. Water finds its way eventually to rivers and then into the ocean. And that generic cycle, you really should have learned in some way, shape, or form. But if not, we'll go over that after, let's see, in 2 weeks. Next week. Our atmosphere is mostly warmed from the surface of the planet. Bless you, I think that was a sneeze.
Yes.
Your oceans, your rivers, your lakes, your surface water is mostly heated up from the sun. But most of the energy and the heat from our planet comes from up in the sky. There is some that comes from the planet itself, and there's also some that comes from the interaction of the tides, the friction of the tides themselves. Yeah, this hydrosphere atmosphere interaction section, I'm glad that 6 weeks exams are splitting it in between because it's a bunch. Okay, we've talked about the snow albedo effect. Okay, albedo means it's reflecting back into space. Most of the infrared, the incoming incident, it's been a while since we've viewed, that's what incident means, coming from space to the earth, coming incoming. 30% of it is bounced straight back out to space. Now, some of it's done by clouds. Things that are white reflect light. Things that are dark absorb light. So ice and clouds, so the caps, the tops of mountains, the clouds themselves reflects, give or take, 30% of the incoming infrared, the stuff that heats up our planet. The stuff that does make it through, if it hits something with low albedo, water, liquid water, land, okay, not light-colored land, darker colored, so grassy areas, forested jungle areas, darker areas, that tends to absorb more of the light. It still reflects some, but not as much. Don't worry, we're not going into like the math of this. Higher albedo, which means it's going to reflect more, would be ice, okay, so solid water in light, paler areas like deserts. Now, I know some deserts have darker red sand, some have lighter sand. I understand they're different colors, but in general, desert areas have a lighter surface color than like forested, non-arid areas. Higher albedo reflects more, lower albedo still reflects some, but it actually absorbs more of the heat. Roughly twice as much light is reflected back into space in the infrared. Okay, so the high albedo reflects approximately twice the amount of the light as the low albedo. Like I said, I left the mathematics off of this. That's not really worded very right. The roughly twice as much is reflected back goes with high albedo. It compares the two. Let's see if I can't fix that. If I remember to fix it. I won't remember to fix it. Anyway, I'll forget. You wait till y'all get old and your brains don't work right anymore. Horrible. All right, so most heat added to the earth comes from above the hydrosphere. Okay, I just said that 99.98% of the heat that affects this earth comes from space, comes from above the atmosphere. Solar radiation, this is like from space, from the sun, is 99.98%. Internal heat from the earth itself, like geothermal activity, hot springs, lava, that kind of stuff, is 0.018%. And then the last teeny tiny bit is the friction of the different currents in the ocean. Tidal energy, the way that the friction between the waves and the shore itself, the more movement, the more friction, the more energy, the more heat. But it's not like the oceans are going to boil at the shore because the waves are crashing there. It's not that much. So very, very, very little bit from the ocean, from tides. That's the last thing that we're doing on Friday. And we actually have already done tides a bit. That makes them a lot shorter. Because I'm not going to go back in depth over neap and spring tides and the way that the moon and the sun pull. I mean, I'll talk about it again, but we've already done it. Let's see. If we have greenhouse gases, specifically water, which is a greenhouse gas, believe it or not, carbon dioxide, the more of that that's in the atmosphere, the more heat is trapped. They let the stuff come in. They let the infrared, they let the sun's rays come in, but they don't let it escape. And so some energy is because of what you call global warming. They are greenhouse gases. And we, in the 6 weeks, get to do a little bit of evil bad human right towards the end. What we are doing as a species, not necessarily in this country, because with EPA and things like recycling and stuff, Americans tend to, not everybody, but we tend to be a little bit more conscious of the environment around us. In fact, I'm going to put solar panels on my house. I already have a solar generator. Little itty bitty thing. Camping. It'd be nice to have no electric bill. Right. Link systems. I think we've mentioned some of these before. I don't know if it was this one. This is the interaction between water and carbon dioxide. There are many different environmental systems that are interacting with each other. The big one that we're going to talk about in a couple weeks is the water cycle. We're eventually going to talk about the carbon cycle. I think we're going to do the nitrogen cycle in there too. We've already done the rock cycle. There are these loops that keep going over and over and over, and as long as they don't get out of whack, they take care of themselves. The more water vapor Okay, it's not like it's an ocean in the sky. The more water vapor in the air, the more carbon dioxide in the air, the more heat's going to be trapped from our Earth, because these are both greenhouse gases. IR is infrared. If you don't remember, it's been a while since we've done the spectrum. It was the first 6 weeks. The more, obviously, the more it holds on to. Doesn't happen in an instant, but the more it warms up, takes time, and over enough time, we could eventually have another thermal maximum where there's zero ice on this planet, back between the Paleogene and the Eogene. And horses were first starting to figure it out. Now, water, if it's in check, if it forms clouds, it actually bounces some of the infrared back into space before it comes in. So water vapor, even though it's considered a greenhouse gas, is a check on carbon dioxide. Because if you have enough clouds, it's going to stop it in the first place. Because it hits those white clouds, white is a reflective color, bounces it back up. Y'all remember the only reason why clouds look gray, right? When you're getting ready to rain, why do clouds look gray? Because they're not really gray. They look at, what? No. Why does the underside of a cloud look gray or even black when it's getting ready to rain? It's not,
It's the shadow.
it's the shadow, because the sun can't make it all the way through. It's not really that color, it's, we see the shadow. We learned that too, Kaden. Oh. So as long as, once again, IR is infrared, the clouds are a check against the carbon dioxide, and as long as these two are in successful limbo, that means one isn't really winning the battle, they're just sort of playing tug of war, and that flag's just moving back and forth, then we have a check on our planet. The problem is that we're pumping so much gosh darn carbon dioxide into the atmosphere because we like our cool toys. And it takes a lot of carbon dioxide as emissions to make in production all these cool toys that we have, specifically anything made of plastic. Plastic comes from petroleum byproducts. And if you didn't have it, you didn't have oil, you wouldn't have anything from toothpaste to paint, to basically anything in the medical field. This world is soaked in oil. And I don't mean like you're literally pouring it on your head. I mean, it's in everything that we use. Everything. Oh, I forgot to animate this. Well, crap. Let me fix this. Glad I got them all. Apparently I missed this one. By paragraph and get rid of that. I just animated my slides this morning. I forgot to do it yesterday. Busy yesterday with Easter and everything. Okay, we're going to get more into these surface circulation patterns. You've got ocean currents, and we've got anything from the currents to the streams. We've got what are called gyres. We've got subsurface currents going on. That's more for tomorrow with ocean currents. But we also have circulation patterns in the air, in the atmosphere, that are completely correlated with the motion of the currents that are in the oceans. It's called the Coriolis effect, and we have a whole separate section we're going to talk about that. I have to bring it up tomorrow because the Coriolis effect is a result of the spinning of the Earth and then the patterns of the different currents, the gyres, the circular patterns, not the streams. The streams are more for trade winds. So much stuff to learn about that, and I had to somehow smash these things down into hopefully 30 minutes. This is the long one. You have clockwise in the northern hemisphere, okay? And then you have opposite counterclockwise in the southern hemisphere. You flush the toilet in the northern hemisphere and it spins this way. You do it in the southern hemisphere and it spins this way. They're opposites of each other. Winds do the same thing. Now, we do have alternating bands of winds as you change your latitude. I don't think I go into that today. I'm pretty sure I go into that tomorrow. But in general, like hurricanes, they spin a certain way. Low pressure spin counterclockwise, and they pull in. In the southern hemisphere, they would spin clockwise. They would still pull in because it's a low pressure. Once again, we have already done this. I'm just pulling everything together. Stratification. Stratification means layers. Fancy science geology term for layers. Your surface layer, holding tank is does not mean like a pool, like an ocean, like a reservoir. You've got the surface layer that is going to exchange heat with the atmosphere because it's at the surface where the air starts and the water ends. This is called the mixed layer. In between the surface layer and the lower layers, the deep layers, we have what is called a thermocline. I'm going to get into thermoclines and haloclines a little bit more in depth later. I can't remember where I built them in. They're somewhere in the notes. At the thermocline, you have a very dramatic change in temperature the deeper you go. That is not so much in the surface area. Yes, there's a change in temperature a little bit, but it's a lot more consistent, a lot more steady. Below the thermocline, the deep layers, these have their own current system going on. It's more controlled by salinity. We'll get into that later, like percentage of salt, how dense is it? And your deeper layers, as long as you don't have upwelling, which we'll get to later, they're going to not be exposed to the atmosphere for a long period of time. They tend to have a much lower oxygen content. I got one more. Hopefully you guys all did your prompt thing, because that's what I used for attendance. Just started checking it this morning, actually reading them. Like I said, we're doing water for a while. Let me check one last one. No. Oh, wait, there's Sarah. I do see Sarah. I don't think I saw Sarah before. Too many papers in front of my face. Sarah, I got it. Last one. With lakes tend to be much more shallow. Yes, I know there's some lakes that are a lot deeper. The rolling current, which brings the temperatures to more of a constant state, it's all temperature control. Warm things rise and then cooler things tend to sink. It makes a rolling motion. Like if you boil spaghetti, you see how it's like moving in a circular pattern. This is 100% controlled by seasons. So warmer things are less dense, they're going to rise. That is called epilemion. I don't know if I'm saying that right. I forgot to Google it to let it pronounce it for me. The colder weather hypolimnion, that has to be the way it's pronounced. It's the way my medical terminology brain is reading it. With oceans, your shallow currents are actually driven by the wind. We've talked a little bit about currents before, and I know I mentioned riptides. If I failed to do it, eventually I will talk about riptides. Those are the ones that drag you out to sea. You look and you can see them from the shore, so I don't understand why people go into them, but maybe they don't know that's what they're looking at. Your deeper currents are driven by the density of how much salt is present. The denser, the more salt, it's going to sink. The less dense, it's going to float. It's also controlled by the shape of the ocean basin, which is originally what I wanted to do Friday, but I've pushed that out. I don't know where I'm going to put ocean basins at. So let me freeze this. And let me stop this. Stop the recording so I can throw it into Canvas.